Last time I introduced the double integral and extended the definition of the double integral already to general regions. So that's the last thing we have done. And for general regions, we divided them into so-called regions of type 1 and regions of type 2, which are essentially the same. You just change the x-axis by the y-axis. So this is just a different way to see a region. Now, the last thing we have done last time, I discussed some examples. So let's maybe look at some more examples. Actually, until now, the only motivation for defining the double integral was in case where the function is larger or equal than 0. So we have a function of two variables above some region. And if the function is larger or equal than 0, then we have a solid which is given by everything which is below the graph of the function and above the xy plane. And our motivation for defining the double integral was to find the volume of this solid. We haven't seen other applications of the double integral yet. So maybe let's use the double integral to find the following volume. So find the volume of the solid bounded by x squared plus y squared is equal to 1. So this is a circular cylinder. Then the plane y is equal to z. Then the plane x is equal to 0. The plane z is equal to 0. And in the first octant, okay, so if you have to solve something like this, an example like this, the first thing you certainly want to do is you want to plot a picture, which is not so easy because we are in the three-dimensional space. Okay, so, but just roughly, so x, y, z. So we have this plane here. Okay, y is equal to z. So this is kind of this plane here, which so I just draw the projection of the y-z plane. So we have this plane here. And we have the cylinder x squared plus y squared is equal to 1. Okay, so this is the cylinder. So we see that if we use this plane here, okay, we slice the cylinder into two parts. Now we have more conditions. So x is equal to 0, which means the yz plane. Z is equal to 0, which is this plane here. So what is left is only this wedge here, which you see here. So from I should try to at least try to. This kind of wedge here. And since we have the requirement in the first octant, it's not the one which is behind this one. It's this one. Okay. So if you have given such an example, the first thing you certainly want to do is you want to understand, roughly understand how the solid looks like. Now, if we want to use a double integral in order to compute this, okay, we have to because we are looking at it from this here. So we project it down on the xy plane, but we see projecting down on the xy plane, so the domain over which we have to integrate is just given by this circle here, okay, which is given here by the of this a quarter of a circle, which is given here by the circular cylinder. So what we have to do is, okay, the unit circle. So we have to integrate over this region here. So this will be our D. Okay, so the volume is given by the double integral over D, and you see we have to go up to the plane. Okay. So we have exactly here, we have given this function here, z is equal to y, and we have to compute the volume of the solid below this function, below the plane, above the xy plane, okay, and which is bounded by this region here. Okay, so we have here y dA. Okay, and for this here we use our usual. So you can interpret this as a region of type 1, but you can more or less forget about this. So the way we look at this is, okay, you first decide which direction. So let's say first the outer integration along the x-axis. So we go from 0 to 1, and the so this means here we fix here some value between 0 and 1, and then we have to go with y from 0 up to this point here. So the square root of 1 minus x squared, and then y, and now dy dx. Okay, so this is the integral from 0 to 1. Now the inner integration, of course, is easy. So what we get is we have here 1/2, and then we have y squared. So we have 1 minus x squared dx. Also, the outer integration is not complicated. So we have 1/2 minus 1 over 3, so 1 over 6, which is 2 over 6, which is 1 over 3. Okay, so you see, such examples are not very complicated. The only thing you have to first try to understand how the solid looks like. So make a picture, then decide, project the solid down on the xy plane. Then you get this region D here, the plane region D, and you have to integrate over this plane region. And you have to decide also from where to where, because it's not always that we have. Sometimes we have also a part which is below, and so on. Okay, so this is one easy example. Now another one. Sometimes it's not necessary. Okay, that's sometimes it's better if you rename here the axis. Okay, because of course the way we look at the moment at things is okay. So we have some domain in the xy plane, and then some function of f of xy, and we integrate over this function. Okay, but sometimes it's, if you have to do such volume computations, it's better to first kind of relabel the axis. One example for this is this example. Okay, so find the volume of the solid enclosed by x squared plus z squared is equal to r squared, and y squared plus z squared is equal to r squared. Two cylinders. Okay, I think we have discussed this example last semester. So this is a little bit hard to depict. Okay, so you have one here. So you have, it's not easy to plot this because you have one cylinder here. Okay, so this is the cylinder, this is this one, and you have another one here. Okay, and those two, so you because they have the same radius, so you have one cylinder here and another one perpendicular to it, and they have inside, so they will enclose a solid, and we should find the volume of the solid. Now, here you have to realize something. It would not be good to look at the situation like this here. Because if you look at the situation like this here, okay, the projection of the xy plane is just a square. Okay, so what you have is, if you look here at the projection onto the xy plane, is a square. Okay, because this will be one cylinder and this will be the other one. Okay, and here you have r, here you have minus r, here you have r as well, here you have minus r. Okay, so you can imagine you have here one cylinder and here the other one, and you have a z direction. But for this, if you look at this, of course possible, okay, but more complicated. If you look at the situation like this, okay, then it's not so clear because if you have this point here, it's not so clear, okay, what is the corresponding z value? Because it's roughly speaking, you will have this line here, and you will have to use a different cylinder here and here. Okay. So it's much easier to interpret y as your new z axis. Okay, because or x it doesn't matter. So let's say x is our new z axis. Okay. Because then the projection onto the yz plane is just a circle, okay, and it's much clearer, okay. If you fix a point in this circle, it's much clearer what is the corresponding. If this is now a z, the corresponding z value, okay, because you just take the other cylinder. Okay, so you have to realize here it's good here to for this example it's good here to relabel, for instance, like this here. Okay, this makes the situation easier. So you interchange z and x. Okay, then here you do nothing, but here you have this. You replace this one by y squared plus x squared is equal to r squared. Okay, because then the projection onto the xy plane is a circle with radius r. And it's much clearer, okay, what the corresponding z value is, because the corresponding z value is just given by this here. Okay, so you see, it's a good example because it tells you that sometimes it's better to change your point of view. Then the example can get much easier. Okay, because then you don't have to think too much. You can easily write down the double integral. Actually, you see that because we have here 4 pieces and we have something above and we have something below. So we have overall 8 pieces and we just have to go over this here. Okay, so we have 8 times the double integral over this region D, and what is the corresponding z value? The corresponding z value is just this one. Okay, so our function becomes the square root of r squared minus x squared dA. I hope you understand what I'm talking about, because I'm not so good in drawing this kind of stuff. Okay, I'm using too much maple, so I don't know how to draw this kind of stuff. So I just can describe, okay, what I want to do. But actually, this kind of solid is of course hard to draw. Now this integral is easy to solve. We have 8 times. Okay, so we have to integrate over this piece here. So for instance, x from 0 to r, then y from 0 to the square root of r squared minus x squared. And our function is this one. Dy dx. Okay, so you see this is 8 times, and then the integral from 0 to r. This doesn't depend on y, so the inner integral is easy. So we have r squared minus x squared dx is equal to, and now, okay, so what do we get? 8 r to the cube minus, and then from this one we have 8 over 3 r to the cube. Okay, so overall, what do we get? R to the cube. So this is 24/16. You see like this, the example becomes very easy to solve. You can try to solve the example where you do not change your point of view, meaning that you do not change the role of x and z. It's also possible, okay, but the function here is harder to determine. Okay, so this is how such examples are solved. So the first thing normally is to you try to depict or you try to plot the solid, and then sometimes it pays off to think which of the three coordinate axes do you interpret as your z-axis. Then you project the solid onto the xy plane. This gives you the region, and you figure out the function, and you write down the double integral, and the rest is automatic because we know how to solve double integrals, in particular because we have the theorem of Fubini, which tells us that, okay, a double integral for us is, in most of the cases, easy to solve because it is just the iterated integral. So we have just to apply the rules we have learned last semester. Now, another important observation is the following one. Sometimes iterated integral can be solved by changing the order of integration, whereas if you do not change it, it wouldn't be possible to solve it. So for instance, this one. So the inner integral would be complicated to compute here because we compute integrals, single integrals, by using the fundamental theorem of calculus, which tells us, okay, first find the antiderivative and then evaluate it at the upper limit minus the lower limit. So, but here for this function, the antiderivative complicated. Okay, so this looks like, okay, we cannot solve the inner integral. Okay. Now the only thing you have to do here is you have to observe that if I change the order of integration, then things get more simple. Okay, so for this you first try to figure out, okay, over what is the region over which the plane region over which we integrate. Okay, so we have here the function x is equal, because x is equal to square root of y is equal to x squared. So we have this function here. So this is the function y is equal to x squared. We see because here 0 to 1. So we look at this part here. So this is 1, this is 1. And we integrate from y from 0 to 1, and then we go from x from the square root of y to 1. So what we do is this is our domain. Okay, now we know that, okay, because this function continues, so we can actually interchange the order of integration. We get the same value. If we interchange, okay, now first x goes from 0 to 1, and now y. So you fix here an x value, and then you go along y, but y goes from 0 to x squared, and then you have this here. Now you see the inner integral does not depend, because the function does not depend on x. So the inner integral, okay, does not depend on y. You can take this out, this is a constant, and you can solve the inner integral now. Okay, but now you can also solve the outer integral, because this function here is the inner derivative of this function here. Okay, so what you get is 3/2 over 3/2. So what does this give you? This is the inner integral is 3x squared, so I have a 1 over 3 evaluated at 0 and 1. Okay, and this will give you some value. Okay, I'm not going to compute it. But the important thing is, okay, you observe here, if the order of integration is like this here, you cannot compute it. Okay, because you cannot find the antiderivative of this function, and in fact it can be proved there. Using the functions we know, there is no antiderivative of this function which can be there is an antiderivative, of course, but it cannot be expressed in the functions we know. Okay, so like this integral cannot be solved. Okay, in this sense. Okay, but if you change here order of integration, this can be solved. This will help us because this we will see some examples in the assignments. This will be useful even for solving single integral. This will be useful in many situations, okay, where we have given a complicated integral, and this will, in particular, yield to, give some useful results also for single integrals. We will see this in the assignments. Okay. So sometimes, if you cannot solve the integral, the iterated integral like this, try to interchange the order of integration, and you might be able to solve it. Because we defined the double integral now for general regions, and in fact there are now many properties which we have seen already for the double integral over rectangles, which hold as well for a general double integral over general regions. So for instance, you have that if you have a sum of two functions or a difference, then this is the sum of the double integrals. Or a difference of the double integrals. If you have a constant times a function, this will be a constant times the double integral. If you have two regions, D1 and D2, where those two regions, okay, are disjoint, so they do not have a common intersection, okay, maybe except on the boundary, okay, so maybe they touch on the boundary, okay, then you can merge those two to one, where you have the integration over the union of those two regions. This is sometimes helpful, okay, because if you have a region which looks like like this here, okay, so you can use this property in order to, because this region is not type 1 because of this nose here, and this region is not of type 2 because if you look at it like this here, no, this region is actually if I plot it like this, it is actually of type 2. So maybe I have to add here something different. Okay, now it's not of type. Now it's not of type 2 either, but obviously you can divide the region, okay, such that, for instance, you go from here to here. Now this is your D1. This is type 1, and this here, the remaining one, would be type 2, and you can compute the corresponding double integral, okay, by using our results for type 1 and type 2 regions. Type 1 and type 2 regions are the regions we more or less can handle. Okay, so this property, okay, it's not so complicated to prove, but also not so easy because you have to go back to the definition of the limits, and you have to carry through the definition in order to see whether things work out. This is just a technical detail, but I guess you will certainly believe me that this property is true. Now, another property is okay. So if you have, if your function is equal to 1, then what you get is just the volume, the area of D. If you do not have units, okay, if you have units, you do not get the value you get is the area, but the unit is not correct. So also this is an easy property, and if you know that your function is bounded from below by m and bounded from above by a capital M, then this follows from this property. And if you have two functions f and g, f is smaller or equal than g, then the integral over f is smaller or equal than the integral over g. So this will be larger or equal than m times the area of D, and smaller or equal than capital M times the area of D. Okay, so you have this kind of inequality, which sometimes is useful in order to estimate integrals which you might not be able to compute. Okay, so for instance, an example for this last property, e to the x square plus y square dA, where D is you see, without doing any computations, you can get already. So this will be larger equal than 1, and smaller equal than is at most e to the 1 over 4. And without doing computation from this property, you would get already that the double integral is larger or equal than 1 times the area of the region, but this is just a circle with radius 1 over 4, so 1 over 4 pi, and smaller equal than 1 over 4 pi e to the 1 over 4. Okay, so you don't have to do computations for this. You can immediately get this result. Okay, now the next thing we want to do is sometimes you have given a double integral which you should solve, and the region is given as follows. Okay, so sometimes you might have given a double integral, and for instance, the region is given by, let's say, for instance, some part, this part here of the circle, or something like this here. Where the inner radius R1 and the outer radius is R2. Now, you observe that this kind of region, okay, if you change to polar coordinates, then this kind of region is getting very easy, because in polar coordinates, this region D here is just a set of all R theta, such that, okay, the R is between R1 and R2, and the theta is between 0 and pi. So actually just a rectangle. Okay, so this is in polar coordinates. This is just a rectangle. So actually this kind of region is not very complicated in Cartesian coordinates either, but in polar coordinates it becomes much more easier. That's why you might be interested to know, okay, if you change from Cartesian coordinates to polar coordinates, what will happen with the double integral? Okay, this will be our first instance of a because this is a kind of, because we know that polar coordinates, okay, you have x is r times cosine theta, and y is r times sine of theta. Okay, and this will be our first instance of a substitution. Okay, and we will later on we will learn a general rule how to do substitutions for double integrals for general functions here. But in this here we first look at a special instance where we have a polar where we use the polar coordinates, where we use a substitution which is of this form here. We introduce polar coordinates because sometimes, of course, this might here, if you integrate over this d here, this makes the region easy, okay, but it doesn't necessarily make the function easy, okay. So maybe the function is getting more complicated, and then it doesn't have any value. But we will see many examples where the function is also getting easy, and then this can be carried out. So we are interested to know, we want to know if we change from Cartesian coordinates to polar coordinates, what does happen with the double integral. Now, for this, we look at the following problem. So we look at the general polar rectangle. So this is a special case of a polar rectangle. We assume, first of all, we assume f is larger or equal than 0, because we know if we have this case, then we are talking about the volume of a certain solid. Now, and we look at the d, which is so-called polar rectangle. So you have here some angle alpha, and you have here another one beta. And we have the easy situation where we go here from some, let's say, A to B. So our rectangle, or our D, in polar coordinates is given by AB. So this is for the radius, and alpha beta. This is for theta. Okay, so we have something like this here. So you can consider, you can interpret this integral as the volume of the solid, okay, which lies above this region, okay, and is bounded from below by the xy plane. Now, the idea in order to compute the integral is, of course, the same as always. We will divide this polar rectangle into smaller rectangles, polar rectangles. So what we do is, okay, we divide AB into, let's say, n subintervals of length delta r, which is b minus a over n, and we divide alpha beta into m subintervals of length let's say delta theta, which is beta minus alpha over m. Okay, so this means, okay, we have a certain subdivision here. So let's say this is the ice radius. So we have here from, so this here is the polar rectangle, which is given by ri minus 1 ri times, and then theta j minus 1 theta j. Now what we do is we choose a sample point, okay, in all of those small polar rectangles, okay, and we choose the midpoint, okay, of this interval here. Okay, so define, let's say, rij as I don't have to add this, so ri, let's say bar, as ri minus I minus 1, sorry, plus half, and theta j as theta j plus theta j minus 1 half. Okay, so this is one of the, we choose a sample point. In other words, we choose a sample point here inside. Okay, and now what we do is, okay, so the volume which is of the solid which lies above this piece, okay, is what we call the ice volume. Okay, actually 2 indices, ij. Okay, you can approximate it by, okay, so because we have what is the height? Okay, the height is of this so you look at the solid, okay, above this piece here, okay, and as height of the corresponding cylinder, you choose f evaluated at the sample point. Okay, but we use polar coordinates. So we have f of ri bar cosine theta j bar, ri bar sine of theta j bar. Okay, then and multiplied with the area here. Okay, this gives you the cylinder. This gives you an approximation of the volume above this piece here. Okay, but the area here of this is of course easy to compute. It's 1/2, and then you have because here we look at this interval here. So square times theta. So we from here to here. So theta, delta theta. Okay, because the length of this interval is delta theta. Okay, so this is just the length here. This is the area of the whole piece here. Okay, of this sector, and you have minus 1/2 ri minus 1 square delta theta. Okay, so this is given by our function. I'm not going to write this here, and for this you can take out. So you can write this as you can take out delta theta. You can take out 1/2, and then you have ri minus ri minus 1, and you have times ri plus ri minus 1, and everything times 1/2. And you see that this here is our delta r, and this here is what I call ri bar. Okay, so this gives you here just an approximation of the solid, okay, lying above this piece here, okay. And now you add over all pieces. Okay, so it's always the same idea. You have you want to integrate over the region D, which is given by this polar rectangle here. You divide it into smaller subrectangles. On the smaller subrectangle, you approximate the solid by a cylinder, which is and the cylinder has this here as a base, and the height is given by f evaluated at the sample point, to sum over all those pieces. It's approximated by the sum I from 1 to what did I say, n or m? N. The sum j from 1 to m of all those dij's. Okay, and I plug this in, so what I have is, okay, so this is equal to the sum I from 1 to n, the sum j from 1 to m, and here I have f, and then I have r I bar cosine theta j bar, and then r I bar sine of theta j bar, and this here becomes delta theta delta r, and I have r I bar. And now you see, you recognize this is a double Riemann sum here. So as n and m both tend to infinity, we should get the volume. So from here you see the formula. The volume should be given by the double integral over our original domain, and then f of r cosine of theta, r sine of theta. This domain is now in polar coordinates. And then you have an r d theta dr. Okay, so I mean I can write here the rectangle, what I have dr. So the r is from a to b, and the theta is from alpha to beta. So this is what happens with the original integral if I change to polar coordinates. You see, what I have to do is, okay, I have to change the region D to polar coordinates. This you see here. I plug in for x and y r times cosine of theta and r times sine of theta. And here you see this, don't forget about this here, and you have an r here. Okay, d theta times dr. Okay, so when changing to polar coordinates, once more, I have to change the region, and I have to plug in for x and y the polar coordinates, the equations for the polar coordinates, and I have to multiply here with an r, and that's the way I can change from Cartesian coordinates to polar coordinates. Okay, so any questions to this? Actually, there is an easy way to explain why we have here the additional r. This way to explain this is as follows. So you think about, because the original, so maybe I should write it, so this is equal to the original integral. You think, so what we do is, okay, we want, because we change to polar coordinates, which means we replace x by r cosine of theta and y by r times sine of theta. Okay, of course we have to plug in here. Okay, that's what we do here. Of course we have to change the region D into polar coordinates. This is what you see here. Now the question is, okay, how does the dA change? Okay, you remember, if we have a function here of one variable, okay, what we do here essentially is substitution. And for such a function, we also, if you have a function of one variable, the substitution rule is, okay, you have also to change the limits. Okay, you have to plug in the new function, and here you also have a change, okay, given by the derivative, okay, of the function which you introduce. Now, here the question is, okay, how does the dA change? And the easy interpretation is, because you can, the dA you can think about this kind of, this very small piece here is the dA. Okay. And you see the angle here, this angle is delta c is delta theta. Okay, and the length here, the length here of this one is dr. Okay, so in the limit you will see that dA should be roughly r times dr times d theta. And this explains why you have to introduce the r. This is something maybe you have seen already in other classes, and because normally people in working in physics or applied sciences, they do the change of variable like this here. So they explain this here. When I was a freshman, I saw this in physics very often, and I couldn't understand why, because this is not very convincing for a mathematician. But of course, intuitively, okay, I can understand. Okay, you can do it like this. But if for a mathematician, this is such an argument is not convincing at all. But it's a good way to memorize why there is an r here. This one, so where D is bounded by x is equal to square root of 4 minus y squared, and the y-axis you see that, okay, the first thing we always do is we plot D. So what we have here is radius 2. And we have just this part here. So so we have this part here of the circle. Okay, so if we change to polar coordinates, so in polar coordinates, this here becomes, so the D will become, in polar coordinates, will become the interval. The r goes from 0 to 2, and the theta goes from minus pi half to pi half. Okay, so if we do the change of variable, okay, so here for this integral, we will get, okay, so the integral now from r from 0 to 2, theta from minus pi half to pi half e to d. Now this will become minus r square, and we have the r, which you should not forget, d theta dr. Now we see that here the integral does not depend on theta, or you can say this, the part of theta is equal to 1, so this becomes a product of two integrals. So this is the integral from 0 to 2 e to the minus r square r dr times the integral from minus pi half to pi half, and then d theta. And you see, because of the r, you can compute this. Okay, if the r would not be here, you would not be able to compute this here. So this just becomes pi, and for this you can compute it by doing substitution. I'm not carrying out the computations. We will see in a similar example a little bit later. Another example: hole with radius r1 is drilled out from a sphere with radius r2. Find the volume of the resulting solid So the sphere is given by x squared plus y squared plus z squared is equal to r2 squared. And I mean, this is not very precise, but if we project everything onto the xy plane, okay, then what you see from the sphere is, because that is equal to 0, so what you see is just a circle with radius r2. And what we drill out is a hole. So because this is not very precise, I drill it out not somewhere, but at the center. Okay. So I get here a hole. So this is the d over which I have to integrate. And the set here is given by this function here. Okay, so what I have here is okay. So I have the volume is given by. I just have to look at some p's. So I just look at this one, and I have everything a times. So a times the integral over d. So this here is my d. Okay, so I have the integral over d, and then the function becomes the square root of r2 square minus x square minus y square dA. Okay, so you see this is not complicated to compute, but the trick is to change. This would not be too complicated either if you do not change to polar coordinates, but you certainly see that there is an advantage changing to polar coordinates. So if you change to polar coordinates, your r is from r2. Sorry, this is r1. Is from r1 to r2. Your theta is from 0 to pi over 4. And this function here becomes r2 square minus, and this becomes here r square. And then don't forget the r. And then you have the theta dr. Okay, and of course this again is easy to compute because you can write this as a product of two integrals. So actually, because everything does not depend on theta, so the integral over theta is pi over 4. So times 8 is 2 pi, and then we have the integral from r1 to r2 of r times, and then the square root of R2 square minus R square dr. And this part easy to compute. Okay, so this is 2 pi, and here I have R2 square minus R square to the 3/2 over 3/2. Okay, so if I compute this, then I have also the inner derivative, so I have 1 over everything is minus, okay, minus 2, and then evaluate it at R1 and R2. And you see only the lower limit remains, so this becomes what? This becomes 2 over 3 pi, and only the lower limit is important, so I have R2 square minus R1 square to the 3/2. Okay, so also this is not very complicated. So you see how to do these computations. We will do more examples in the assignments. Until now, we have just considered the substitution to polar coordinates for regions which become, after the substitution, become a polar rectangle. But of course, you can, again, you can extend this to more general polar regions. So if I have something like, so again, you have an alpha, you have a beta, and you have some function here, so h1 of theta, and you have another function here, which is h2 of theta. So if you have such a general region, given in polar coordinates, this is the region D, and D is in polar coordinates is given by the set of all x, y, r theta, such that, okay, the theta is between alpha and beta, and once you fix the theta, the r is between h1 of theta and h2 of theta. Okay, then similar, the double integral over d f of x, y, dA will become the integral. So you first go from alpha, from theta from alpha to beta, then you go along r from h1 of theta up to h2 of theta, and then you have f of r cosine of theta, r sine of theta, r d theta. Okay, so this is the more general situation, because the proof you just saw before is just for polar rectangles, but it's also true for these more general situations. For this more general situation, and you see that if the function is equal to 1 and h1 of theta is equal to let's say 0, then what you get is just the area of the region here, and you see for this area we have that this is the integral alpha to beta. Now the inner integral is so this is equal to 1. Here we have an r, so we have r square half. So what we have is h2 of theta square half d theta, and this is actually it's a formula we already found last semester when we computed areas of regions, of plane regions. So this tells you can use a double integral, but it should be pretty clear to find areas of such regions just by setting the function to be equal to 1. Okay, so you find some examples in our textbook. Let's look at one example. Okay, so use the double integral to find the area enclosed by r is equal to sine of theta and r is equal to cosine of theta. Okay, so the first thing, plotting a picture. we remember from last semester that this is a circle here of radius 1/2, and this is also a circle of radius 1/2. So you see this because this is given. This is a polar curve, so this is given in polar coordinates. For this one, you see if theta is equal to 0, the r is equal to 0. If theta goes on to pi/2, it's maximal, and then you go back. So what you have here for this curve is okay, this radius, this circle. Sorry. So this is r is equal to sine of theta, and for cosine of theta, similar, but the circle is like this here. Should be the same size. Okay, it should be the same size. So the common region is this one. Okay, and you should use a double integral to find it. Okay, so the function is 1. So so this area here is equal to, actually it's enough to look at one piece because of symmetry, you see, because this circle is the same. So it's just enough to look at this part here. The other one will be the same. So you have twice. Now, first over theta, okay, so your theta from 0 to, you have to figure out, okay, where do they meet? But it's from geometric considerations, because of symmetry, it's easy to see pi over 4. Okay, I think before I did the computation wrong, I just figured out, because I think I integrated, I had before an example, okay, but it doesn't matter, already gone, okay. But before there was an example where I integrated over this part here of the circle from 0 to pi over 4, not from 0 to pi/2. You didn't tell me that the range is wrong. You remember? I already erased it. Okay, so some of the examples I've done before, wrong. Okay, so but for this one, okay, so the theta goes from 0 to pi/4, and the r goes from 0 to the yellow circle. Okay, so to sine of theta. Okay, and the function is equal to 1 because we compute area, and then you have an r, which you should not forget. And then the now the order is important, so dr d theta. Okay, so you see that this is equal to 2 times the integral from 0 to pi over 4. Now for the inner integration, you get sine square of theta half d theta. Okay, so you have the integral from 0 to pi over 4 sine square of theta d theta, and we all know how to compute the integral of such a function. Okay, good. I have some time left. I want to show you a more interesting application of changing to polar coordinates. In particular, this is an issue we haven't discussed so far. So the theory of double integrals is also helpful in order to compute single integrals. So the following integral, we already looked at it last semester, this integral here. This integral is an integral which is if this is an improper integral. So if we have an improper integral, the first question is always, does it converge? But there is no problem here. Of course, this will converge. The reason is because as x tends to infinity and x tends to minus infinity, this function is getting small very quickly. So there should be an area. Now this integral is an important integral in probability theory. So in probability theory, this problem will show up how to compute the value of this integral here, and there are many different methods to do it. One I saw it's even possible to use the definition of the Riemann integral, which is quite complicated because you end up with a complicated sum and you have to argue. There is one proof which is because this will turn out to be square root of pi. So there is one proof which is in particular easy, and this proof uses double integration, which is not very obvious if you look at this problem, because it's a problem. It's a problem we could have tried to solve last semester, okay, because we have a single integral and we have to evaluate it. Now, but this has to be, you have to figure out, okay, which function, okay, and this is the clever thing in computing this, okay. So consider this function here. This double integral, okay, where the double integral is over the whole plane, okay. We haven't defined something like this, okay, but it should be clear how this is defined. I choose any bounded region, okay, and I let the region grow to infinity, okay. And in the limit, what I get, okay, if the limit exists and is the same independent how I do this, okay, then I should assign to this integral the value which is the limit, okay. Now, the trick is to compute this twice and use a different way to compute it each time. Okay. So first of all, by this definition which I just mentioned, okay, so the value of this integral. Okay, so one way you could do it is you choose a rectangle. Okay, so you choose the rectangle with side lengths, let's say 2a. You choose this rectangle, okay, and you let a tend to infinity. Now, if you do this, okay, so we have to compute the double integral over this rectangle, but this is easy. So the integral from minus a to a, we go over x first, then we go over y, and then we have this function here, and then we have dy dx. Okay, but you see that this function here. You see that this function here, because this function you can write it as e to the minus x squared times e to the minus y squared, and this means you can write the whole thing as a product of those two integrals. Now, as if I denote this, let's say I denote this value with I. Okay, so if a tends to infinity, what I get here is I squared. Okay, so this was not helpful in computing the integral, okay, because I cannot compute the I squared, but I know, at least I know this integral must be equal to I squared. Now another way to do it, another way to compute this integral, and we will see if we do it differently, we will be able to compute it. Okay, so now, so again, this integral here. Now, we choose the region different. Okay, what we choose is the circle, or I should say the disk, with radius a. Okay, and again, this should be the limit a tends to infinity. Okay, over this disk here. And here, okay, because of the form here, we change to polar coordinates. So the radius goes from 0 to a. The angle goes from 0 to 2 pi. And then we have e to the minus r squared. And then we fortunately have here an r. This makes it easy. Okay, so dr d theta. Okay, so you see, this here is the limit a tends to infinity. So because again, this does not depend on theta, so for theta you get 2 pi. And the other one is the integral from 0 to a e to the minus r squared r dr. Okay, and this is equal to the limit a tends to infinity, 2 pi. And for this integral, what you get is e to the minus r squared. So if you compute the, you have here minus 2, and from 0 to a. Okay, so this will be equal to pi, and the limit a tends to infinity. Now, if I evaluate this, what do I get? At the lower limit, I get 1, so I have 1 minus. And the upper limit, I have e to the minus a squared. But as a tends to infinity, this here goes to 0. So what I get is pi. Okay, like this I can compute it. So I squared is pi. So I is the square root of pi. Okay, so this helps us to find the value here. You see, this is something quite unexpected, that you can use the double integrals in order to compute single integrals. And this evaluation of this single integral is certainly the most easiest one possible. This would be a very hard problem if we would have considered it if we had it considered last semester, because last semester the only tool, because we cannot find the antiderivative here, so we cannot use the fundamental theorem of calculus to evaluate this. So the only tool we had last semester is okay, you really write out the definition, which is very complicated here, and you try from the Riemann sum, from the limits and so on, you try to figure out, okay, what is the value. It's possible, but very complicated. You see, this is another application of, in general, another application of double integrals, because the only application we saw so far is computing volumes of certain solids. But there are many other applications of double integrals. Another one is in probability theory, where you normally, so what you consider in probability theory are random experiments, so-called random variables, a function where the outcome is random. And in particular, what is important in what you consider in probability theory is as so-called random vectors. Here x and y are both what we call in probability theory random variables. So the outcome is random, and what you want to do is you want to predict, okay, what is the probability that the outcome of this random vector is in some plane region D. Now, the way we do this in probability theory for so-called continuous random variables is we have, for this pair of, in order to describe the random variable, we have a function of two variables, and this function will help us to compute such probabilities. So normally what we give are not those two functions. What we give is this function here. Okay, and this function called the density function must satisfy that larger or equal than 0, and obviously that if you go over the whole plane, then the probability that this random vector is somewhere should be equal to 1. So normally in probability theory we give such functions, and so-called density function. And satisfying this property, and we use this function in order to compute the probability that the random vector, which is described by this function, is in some domain, in some region D. And this normally, so computing this kind of questions, computing such probabilistic questions will lead to solving. So you have to solve double integrals in order to do this. Now, for instance, one example. For instance, I don't know. I guess some of you are from Taipei, so maybe you on Friday evening or Saturday morning you will go to Tsinghua University and take a bus to Taipei. Now, normally what you have to do first is, okay, you have to queue up to get your ticket unless you have bought it before, and then you have to queue up for the bus. And both times are random, okay, because it depends how many people are there. So let's say that queuing up for the ticket on average takes you 5 minutes, and queuing up for the bus takes you on average 10 minutes. Okay, so queuing up for the ticket in average takes 5 minutes, and queuing up for the bus average takes 10 minutes. Now, the function which we use in order to describe, because now you have two random times, okay, x and y. One is for the waiting for the ticket. The other one is waiting for the bus to arrive, and the function f, which we normally use because of some reasons which you will learn in probability theory, which we use here in order to describe those two random events, is the following one. So 1 over 5 e to the minus x over 5 times 1 over 10 e to the minus y over 10. This is the function which we normally use. Okay, and here x and y is larger or equal than 0. Okay, so this kind of x here, this describes you kind of the waiting time for the ticket. This describes you the waiting time for the bus. And this can be used in order to understand, okay, how long do you have to wait. So for instance, if you are interested in, okay, so what is the probability that you have to wait less than 20 minutes, okay, under this situation? Now what you do is, okay, you have to find out the probability. So no matter what this d is, okay, so this probability can be computed as the double integral over d and then f of x, y, dA. This function is 0 otherwise. If one of them is negative, 0 otherwise. Okay, and if you want to know, okay, under this situation, okay, what is the probability that you have to wait less than 20 minutes? Okay, so this means that x plus y is smaller or equal than 20. Okay, so you have to look at this region. So x plus y is equal to 20 will give you such a line, and this will be the region over which you have to integrate. Okay, so where this line is the line x plus y is equal to 20. Okay, so what you will get here is okay. So this is the integral from. So this point is of course 20 from 0 to 20. This is along x. And then the integral from, so now I fix the x, so I have to go up to the function up to 20 minus x, and we have this fxy dA. And you solve this, and I have done this already before I came to the lecture. So I have somewhere the value. Okay, which tells you that the probability that you have to wait under this situation, that you have to wait longer than 20 that you have to wait at most 20 minutes is given by this number here. Or in other words, if you multiply it by 100, you see in around 70. So if you go there every weekend, okay, then around 3/4 in 1 year, around 3/4 of the days, your waiting time will be smaller or equal than 20, and only 1/4 of the time you will have to wait longer than 20 minutes. Okay, so this is another application, because you see that in our textbook there is a section on applications of double integrals. This is actually not part. I'm just introducing this application because you see in this chapter there is other applications which is computing the center of mass and so on. I mean, of course, these kind of applications are easy to understand. But my expertise is not physics, but I'm working in probability theory. So this is more familiar for me. So that's why I introduced this here. And as I said, this is not part of the curriculum, but later on, when we come to triple integrals, we have to discuss such properties, because triple integrals are not so easy to find a motivation for them. I mean, it's not so complicated either, but not a direct motivation, because for triple integrals, and that's what we will do next time. Okay, we will. It's the same question, but you have a function of 3 variables. But of course, you are not computing volumes because you are in the 4-dimensional space. You could say, OK, we want to compute hypervolumes, but it's not a good motivation for introducing, because you might ask, OK, why do I need hypervolumes? So that's not a good motivation. So for the triple integrals, we have to give other motivations. For the double integral, kind of more easy, because we have already, from the start, we have a motivation for introducing the double integral, namely computing volumes. But of course, there are many, many other situations where you need double integrals, like in probability theory, in physics, and in many other areas. OK, so any questions?